Hello everyone. Hello. Uh, am I audible or is there still an echo?
Attending today's session.
I could not hear you. Can you repeat? Yeah, we can start today's session. Uh, I hope more people will join soon. Okay, so let me present my screen. So, are my slides visible? I guess they are. Okay. Okay, so welcome to week 4 of tutorial sessions for fundamentals of micro and nanofabrication. And yeah, so I am Mukta, the teaching assistant for this tutorial session. So in week 4, professor has mainly discussed chemical vapor deposition, and just a minute. Yeah. So for the first problem, we'll start with CVD of Cu2O. So yeah, so basically copper 2 oxide, and we want to grow native Cu2O on copper surface. So somebody has access to Gibbs free energy tables for the various reaction of copper oxidation. They have helpfully given us the attached chart which shows the stable material at a given temperature. So we have been given this chart. So as we know, for any CVD process, or for that matter for any chemical reaction, to check if the reaction will proceed in the forward direction or not, we basically check the change in Gibbs free energy. So if delta G is negative, then the reaction proceeds in the forward direction. So yeah, so based on this data, somebody has plotted this for us, and so it is basically the partial pressure of oxygen versus temperature plot. So so yeah, so say this is the reaction, copper goes to copper 2 oxide, then it basically means that for if the reaction conditions are somewhere over here, then we have copper, but if we meet these reaction conditions, then we get Cu2O, or anything above this will give us Cu2O. So basically if the partial pressure of oxygen is too low, we will not get Cu2O. If it's too high, we might just end up getting CuO. So that is what this graph is trying to tell. Yeah, so the lines represent the boundary where thermodynamically suggests the material should react. So basically the boundary where this reaction would start happening. Another interesting thing to note here is that so this pressure isn't torr, right? So this is very low pressure. Uh, so what is the precursor, is it? So in class, if you remember, there was some complicated precursor that Prof had shown, but here we are just looking at copper oxidation. We are not worrying much about where this copper is coming from. Uh, so for this problem, I am not sure. I just took this problem from one of the questions that we got in assignments. I am not sure what was the precursor used. Yeah, like in class, sir has discussed the elaborate reaction for this CVD process. You can check the videos. Kamal, what is the SCCM values we have to select? What do you mean? So we have not started with the question yet. This is just the background. Let us go to the question first. Right. So the first question is just how we read the graph basically, at deposition temperature of 600 Celsius, what is the range of pressure where you will obtain Cu2O? So basically just it's asking us to read this graph. So they have given 600 Celsius as the temperature, so that is this, and what is the range where we will obtain the product that we desire. So basically they are asking, is it this range or this range or above this, like that. So what would be your guess? So yeah, so this just is about reading the graph. So as I already discussed, so below this we won't get the reaction, above this we will get Cu2O, and above this part we will get CuO. So the second region is the region of interest, so that will mean somewhere around 10 power minus 10 to 10 power minus 15. So just giving approximate ranges will work. So in such kind of questions, the explanation is more important. So you can just tell the from the graph we see that some reaction is favorable. The reaction is favorable only between this window. So at 600 Celsius, this range is favorable. Partial pressure is favorable. Okay, for CO2. So the next question is, suppose I also told you that the system has a roughing pump that can go down to a base pressure of only 10 power minus 3 torr. So basically we are pumping out the chamber, and so yeah, what will happen when we pump out? So initially there was air. When we are pumping out to 10 power minus 3 torr, so we are basically creating a vacuum, so the oxygen concentration in the chamber will reduce. So we have to calculate the level of oxygen expected at that pressure. Okay, so assuming that air has 20% oxygen, can you calculate how much oxygen is present in 10 power minus 3 torr pressure? So total pressure they have given. So yeah, so we know that 1 atmosphere is 760 torr. So this is just basic mathematics now. So if we are going to 10 power minus 3 torr, what will be the oxygen percentage? Just 20% of 10 power minus 3, right? So that will be nothing but 2 into 10 power minus 4 torr. I should not have written. At this level of impurity, can you suggest the range of temperatures? So this is 2 into 10 power minus 4 torr. So this much oxygen is present. So can you suggest the range of temperatures at which CO2O can be reliably grown? So again this is also quite easy now. So if we see 10 power minus 4, it will be somewhere over here. So what temperature will we require? Somewhere greater than 800 degrees Celsius. So if we look at it, if we are not able to go below 10 power minus 3 torr, our reaction will take very high temperatures and it is not feasible. So yeah, so what should be the what should be our next approach? We can either reduce the entire total pressure of the chamber, or we can reduce the partial pressure of oxygen. So say we don't have the pumping mechanism to go below 10 power minus 3. So we take another approach. So what they are saying is, suppose we flush the chamber with 99.999% pure nitrogen for long enough to replace the volume inside the chamber 5 times. So basically they are just putting nitrogen in the chamber. So currently there is some fraction of oxygen present. They will put nitrogen, then evacuate the chamber again, then the oxygen percentage will drop down, then again put nitrogen. So it's like rinsing the chamber 5 times by filling it up to full volume and dumping the contents. So by dumping the contents, what they mean is we again go back to 10 power minus 3 torr. So it's like we put nitrogen in the chamber comes back to atmospheric pressure, and then we again evacuate the chamber. So then the chamber goes back to 10 power minus 3 torr. So since we are putting very pure nitrogen, the percentage of oxygen in the chamber or the partial pressure of oxygen in the chamber will reduce. So now what is the range of temperature at which Cu2O can be reliably grown? So when we had got it down to 10 power minus 3 torr for the first time, we got the oxygen concentration to be, or oxygen partial pressure to be 2 into 10 power minus 4 torr of O2. Okay. Now we are flooding it with 99.99% nitrogen. And the pressure goes back to 760 torr. So now can we first calculate the fraction of oxygen in the first term? So what will be the O2 fraction? The oxygen fraction will be nothing but 2 into 10 power minus 4 divided by 760. So that will give me some number. It's okay till here, right? Mir, what is this answer for 700 or above? You are telling for this question. Can you give an explanation? Like just unmute and tell what is your reasoning. Okay, yeah, there is nothing to, like, if you have something to tell, you can tell, it's okay, right? It's okay. For now, I will go ahead. Yeah. Okay. So, yeah. So, where are we? So, finding oxygen fraction is trivial, right? So, we in the first we had evacuated the chamber, then we put the first round of nitrogen in the chamber, and now we have oxygen fraction of so much. Now we will again evacuate the chamber, then what will be our oxygen fraction? Oxygen fraction after first rinse will be, so this was before, then because we put so much nitrogen, the oxygen fraction became so much. Then what are we doing? So this is the fraction that will be left in the remaining 10 power minus 3 torr also, right? So this was the fraction at atmospheric, at 1 atmosphere pressure, or when the total pressure was 1 atmosphere. After evacuation, like same amount of nitrogen will be evacuated, same amount of oxygen will be evacuated. So the oxygen fraction will remain same, right? So then after first rinse, so this should not be fraction, sorry. So oxygen left in this chamber, oxygen partial pressure after first rinse will be so many torr. That's right. So basically, so this is after first rinse. After second rinse, what will happen? Again, whatever is present, so that will be 2 into 10 power minus 4, 5, 6, 7, minus 7 by 760 into, again we will do a 10 power minus 3 by 760. Right. So after um, every rinse, we will be essentially multiplying the oxygen fraction by 10 power minus 3 divided by 760. Therefore, after 5 rinse, the oxygen partial pressure will be 2 into 10 power minus 4 into 10 power minus 3 divided by 760 time to the power 5, right? So then we can calculate this and get an answer. So this will come out to be somewhere around 10 power okay, I think I have the answer. Yeah, this is coming out of the order of 10 power minus 31. So then we can check 10 power minus 31, it will be somewhere around this temperature. So yeah, so then the temperature we have reduced it significantly from 800 to something around 200 degrees Celsius. So that is the answer. So yeah, your guess was quite good that it reduced the temperature. However, if you want to like get the exact numbers, it's always better to do the calculation. Yeah. So that ends this question. Next we will be looking at silicon CVD. Right. So this is basically we are trying to grow silicon on top of silicon, and we are using hot walled LPCVD. So LPCVD stands for low pressure CVD. So furnace with you have a hot walled LPCVD furnace with a quartz tube of diameter 10 centimeter. So the furnace looks something like this. The diameter is 10 centimeter, so it will be some yeah. So radius is 5 centimeter. I just said 10 centimeter. And hot zone of the furnace. So basically we are heating this furnace, right? So the hot zone is 20 centimeter. This they have given. The furnace is used to grow epitaxial crystalline silicon on 10 wafers, 75 millimeter diameter. So there are some 10 wafers inside, each of which has 75 millimeter diameter, and they have given the temperatures. Wafers are actually stacked. Yeah, so based on this information we have to answer the following questions. At what range of temperature do you expect the deposition on the wafers to be uniform? So we want uniform deposition, and we want to maintain growth rate of 100 nanometer per minute. So yeah, so let us look at this graph. So epitaxially, when we want to grow silicon, we will usually grow it using the SiH4, right? So for SiH4, so we don't need to look at the other graphs basically, we are just looking at the SiH4 graph. At what range of temperature do you expect the deposition on the wafers to be uniform? So some things to note here, we are having a LPCVD furnace which is hot walled. So in case of low pressure CVD, it was taught in the class, like do you remember, is it mass flow limiting process or a reaction limiting process?
Mass flow, ma'am?
Low pressure CVD. to think about it in this way, so whenever we are going to higher pressures, the reaction rate will speed up, right, because we have lot of precursor. When we have lot of precursor, there will be fast reaction. So in those cases, the limitation will be for the precursor to reach the surface by diffusion. But when we have low pressure, the so the reaction rate itself is low. So the bottleneck is not the diffusion, but the reaction rate. So in case of LPCVD, it is actually reaction rate limited. And another thing is that this is hot walled furnace. So when we have hot walled, it is always better. Um, when we have hot walled, we have very high temperature control. Or rather very high temperature uniformity. This is because since the entire furnace is at that temperature, there is no heat leakage from the wafer. So it's like, say if the furnace was not hot walled and I was just heating this wafer, okay, so this is my chamber and I am only heating the wafer, then since the chamber is cold, so heat will radiate from the sides to the chamber and this radiation won't be uniform. So the temperature uniformity is less in cold walled chambers compared to hot walled chambers. So since we have good control of temperature uniformity, we have high so it's better to do our process in reaction rate limited regime. I hope I am making sense. So so there is one more thing, right? So when we are in mass flow limited regime, we have to worry about the gas flow. So is the gas flow uniform across the wafer, uniform across different wafers? Uniformity of gas flow, precursor flow. So we should worry about the boundary layer that is formed on the wafer and all that. But when we are in the reaction rate limited regime, so reaction rate limited growth regime, so in this case we have to control the temperature. So this regime is very sensitive to temperature, because in this case the reactors have reach the substrate very easily. There is no diffusion problem. The reaction is limited by the reaction rate, and this reaction rate is a very good function of temperature. So in this case we have to maintain very good temperature. Now we already have a hot walled furnace, so which can give us very high temperature uniformity. So it is better to stay in the reaction rate limited regime. And also, since they have already given us that they are doing it in LPCVD, if you remember the classes in class, Prof has discussed that LPCVD will usually proceed in the reaction rate limited regime. So from this graph, they have drawn the line, right? So is A reaction rate limited or B reaction rate limited? So if you look at this, so this is the way the temperature is increasing. Okay. So at higher temperatures, the growth rate is showing not much dependence on temperature, but at lower temperatures, the growth rate is a linear function of temperature, or rather a very strong function of temperature. So that is why this part of the graph is the reaction rate limited regime. And this is mass flow limited growth regime. Okay, so that's why. So now, at what range of temperature do you expect the deposition on the wafers to be uniform while maintaining a growth rate of at least 100 nanometer? So 100 nanometer means some 0.1 microns. So it should be always be above this. And second thing is we want uniformity, so we want to maintain, we want to stay in the reaction rate limited regime. So about this, so here it is starting to get mass flow limited, so the range will be somewhere between 850 to 750, I think. Is this clear? Like, there were a lot of things that I told, but like, is the explanation, do you think it is valid? So it's not like we cannot get uniformity in mass flow limited regimes, but there we have to have a good control of the flow of precursors, and also there we cannot stack them axially, because if we are stacking axially and if we are mass flow limited, then the uniformity will depend on how much precursor is flowing to the first wafer, to the second wafer, to the third wafer, like that, and towards the end of the growth will be very low. For so that's why for usually whenever there is whenever we are doing in mass flow limited regime, the wafers will be stacked something like this. So if the gas flow is in this direction, so there will be some boundary layer that is forming, but to mitigate that they will be like in the form of steps or something, but they will never be stacked axially whenever we are doing in mass flow limited regime. But since in this case we are planning to do in reaction limited regime, it doesn't matter as long as everything is at the same temperature. Even if the first wafer is seeing more precursor compared to the last wafer, the temperature will govern the reaction rate. Okay, so let's move on. Suppose we do the deposition at the temperature where the deposition is uniform and growth rate is 200 nanometer per minute. What is the total area over which silicon deposits either the furnace or wafer? So basically they are asking whether the silicon will deposit only on the wafer or on both furnace and wafer. If so, what is the total area of deposition? So what do you think, whether it will deposit only on the wafer or on both furnace and wafer?
In case of LPCVD, both,
Right, you're right. So, uh, so can you tell everyone why is that the case?
because it's a hot wall reactor.
Exactly, yeah. So everywhere the temperature is high, so the reaction will take place at even on the furnace surface and on the wafer surface. You're right. So now let us calculate the area as they have asked. What is the total area over which silicon deposits? Right. So like in the question there were 10 wafers and this dimensions they had given. Based on that, so area for the wafers will be 10 times pi r square. So the diameter they had given to be 7.5, so 75 millimeters, so I will just keep everything in centimeters. So 7.5 0.2 square pi r square. And another thing is, even if I am saying the area of wafers, but we have to consider both sides. It will deposit from this side as well as this side. So I have to multiply this by 2. So that will give me some answer. For now I will just write it down, 884 centimeters square. And then the area of the furnace. basically area of cylinder formula 2 pi RL. The radius is 5. So, the diameter is 10 centimeter, radius will be 5. Length is, so hot portion length they are given to be 20 centimeters. So, based on this it will be 628.31 centimeters.
Ma'am, where you got 7.5? Actually 7.5 upon
In
2.
the question they had given,
It's given,
the
na?
furnace is used to grow epitaxial crystalline silicon on 10 wafers 75 millimeter diameter.
Yes, ma'am.
Okay. Yeah. I should have mentioned it here again probably, but yeah. So, that is given in the question. We just have to calculate the area total. Like once we know this, we essentially know the answer. So, total area is 1512.3 centimeter square. So, based on this question, there is a follow up question. Can you calculate the amount of silane consumed in standard like as at STP, standard temperature and pressure? So, okay, we are saying that silicon is depositing all over this area. So, we have to calculate now how much SiH4 is being consumed. So, to solve this problem I can give you some quantities like maybe like atomic density of silicon we can take as 10 power 22. Other than that, yeah, and STP just here means that like if you have 1 mole of a quantity at standard temperature pressure, it will take 22.4 liters. So, then now we have to calculate the volume of silane that is being consumed. So, how much volume of gas was consumed? So, to do that, we know the area and we know that we have deposited, sorry, it is given here only, we have deposited 200 nanometer, we are depositing 200 nanometer per minute. So, in 1 minute we have deposited 200 nanometers of silicon. So, how much volume will be, so to calculate the volume, we just multiply the area with the thickness, right. Volume of silicon deposited will be nothing but so in a minute so much of silicon will be deposited. So, but we do not have to tell the volume of silicon, we have to tell the volume of silane. So, for doing that we look at the atomic density of silicon. So, from here, so there are 10 power 22 atoms in 1 centimeter cube. So, how many atoms are present in so much volume? We can do that, right? Let's do some other color. So, number of silicon atoms. So, just note that the number of silicon atoms will be the same as number of SiH4 atoms or SiH4 molecules, sorry. So, number of silicon atoms we can find out. So, that will be nothing but so this is 3 into 10 power minus 2 into 10 power 22. So, I can just write it as 3 into 10 power 20. Basically, I am just multiplying 3 into 10 power minus 2 times the atomic density. So, so many atoms in 1 centimeter cube. So, in 0.03 centimeter cube, we will have 3 into 10 power 20 atoms. So, this is the same as number of SiH4 atoms. So, but they are not asking it in terms of number of atoms, they are asking us it in terms of volume. So, from the number of atoms, how do we get volume? So, we know that 1 mole has 22.4 liters. I think I should take a different page. It's okay, I'll manage.
And ma'am, can you please write the formula of area of wafer?
Right, just pi r square.
Okay, ma'am.
So, this is pi r square. There are 10 wafers,
Hmm.
and each wafer I am taking it both the sides. So, that is this 10 and 2. So, the total area of all the wafers is so much.
Yes, ma'am.
Okay, right. Similarly, area of furnace is 2 pi RL. So, furnace we will just consider the inside part, right, because only that part is seeing the precursors. So, that gives me the total area. Now, we are trying to calculate the number of, so we have got the number of SiH4 atoms. Till here it is clear.
Yes, ma'am.
Okay. So, from the number of SiH4 atoms, I can calculate how many moles of SiH4 I have. So, number of moles will be nothing but 3 into 10 power 20 divided by the Avogadro's number. So, what is Avogadro's number? 6 into 10 power 23 something. So, this will be nothing but 0.5 into 10 power minus 3, or I can just write it as so many moles, and I know that 1 mole has 22.4 liters. So, this many moles will have how many liters? Therefore, volume of so again this is in liters. For converting from liters to centimeter cube, we just multiply by 1000, and that will give me 11.2 centimeter cube. So, in 1 minute I would have deposited I would have consumed 11.2 centimeter cube of silane, SiH4. So, just to recap, first we found out what is the area that silane will deposit on. Next, we calculate what is the total amount of silicon that will what is the area on which silicon will deposit. Next, we calculate what is the total volume of silicon deposited. So, for volume we just multiply area with the thickness. So, we get the volume of silicon that is deposited. From the volume of silicon, since we want to find the volume of silane, we first calculated the number of atoms of silicon that were deposited. For this we use the density of silicon, that is 10 power 22 atoms per centimeter cube. So, from that we got the number of silicon atoms that are deposited. From this we calculated, from this we said that it is the same number of silane atoms that were consumed. So, from the number of atoms we calculated the volume by using this relation. So, from the number of atoms we can get the number of moles, and for 1 mole we have 22.4 liters. So, for 0.005 moles how many liters, and then we got this number. That's it. Can I move forward? Okay. Uh, if you have any questions, please ask me to stop. Okay. So for the next problem, it's a continuation. In an actual reactor, the SiH4 flow rate needs to be more than this minimum amount. What problem do you foresee if silent flow is restricted to this minimum amount? So they are saying, uh, so we have calculated the minimum, so we have calculated the amount of silent that will be consumed. So this is the minimum silent that we should put so that we get a 200 nanometer per minute deposition, right? So they are saying that even though this is the minimum, so we got that 11.2 centimeter cube is the minimum volume that is required. They are saying that this flow rate of silane should be more than the minimum amount, the actual rate that we put during the deposition. Why is it so? Like they are asking us why that might be the case. So if you remember, we are putting gases in a chamber. Okay. So and the wafers are stacked axially inside the chamber. So now can you see a problem if I just put 11.2 centimeter cube of SiH4 in this chamber? Uh, will it be possible to deposit 200 nanometer across all the wafers? Just try, right? This is quite simple. Uh, okay, so basically the problem that will come is that if I am just putting 11.2 centimeter cube, the first wafer will see the required volume, but as we are as we are progressing, because silane is getting deposited on the walls, on the wafers, everywhere, so there will be a gradient of SiH4 concentration as we go along. So the last wafer, uh, the the amount of silane that reaches the last wafer will be pretty low compared to the predicted value. So because of that, the uniformity will be lost. So we won't get wafer to wafer uniformity in our deposition.
Ma'am, one question.
Hmm. Ask. Yeah, come
Yeah, actually, somewhere maybe it will be asked like to obtain the high growth rate, we have to increase the pressure of the precursors. Okay,
Right. Yes. Hmm.
but
Hmm.
mostly in the case we have two system, APCVD system and LPCVD system.
Right.
So in LPCVD system, major role is played by the precursors.
Hello.
Hello,
It's
my voice is coming.
yeah. It broke in the middle. In LPCVD system, what?
Okay, okay. Yes, ma'am. In LPCVD system, we are temperature dependent.
Yes. Right. Hmm.
Yes. So, ma'am, my question is actually in MCQ. It's there to obtain high growth rate. We have to increase the partial pressure of precursor, but nowhere it is written whether it is LPCVD or APCVD.
Uh,
That's the confusion.
I am not sure, but
Okay.
whenever we are trying to increase the pressure in
Hmm.
low pressure regime, the basic assumption is that the pressure is very low. That's why it's more temperature dependent.
Okay.
Huh.
Okay, ma'am.
I don't know. I, sorry. Huh. Okay. In this question, there is no doubt, right?
No, this is okay.
Okay. Maybe they are asking in a general sense, like if you increase pressure, uh, what is the consequence to the reaction? Whether it is limited by the pressure or the temperature, that they are not worrying about. Like that will depend on the chamber and everything. But in general, what is the answer? Like what is high pressure giving more rate or low pressure will give more rate? Like that.
Yes, ma'am.
Okay. So now the second part of this. Okay. Yeah. Suppose you need to flow silane at 10 times this minimum flow rate to prevent the problem discussed above. So just now we saw that the uniformity will be compromised if we are putting only 11.2 centimeter cube. Now suppose you need to flow silane at 10 times this minimum flow rate to prevent the problem discussed above. So we have, since they are just saying that suppose we have to put 10 times this volume. Furthermore, suppose we have tank with 10% silane diluted in hydrogen for safety reason. The maximum flow of silane that the mass flow controller will allow is so much. Now can we achieve the target growth rates? So okay, so let's go one by one. Suppose we need 10 times more uh, than this amount. So we will need how much? 112 centimeter cube per minute of SiH4 flow rate. Next they are saying is, suppose we have a tank in which it is 10% diluted. So now we need how much of 10% diluted SiH4 will we need? Obviously 1120 centimeter cube per minute. But
In
if
question it given, ma'am, 112 something.
no, like previous case we uh, okay, in this question we calculated this. So the idea was here was to calculate the amount of silane consumed, and we saw that we consumed. So I'll
Yes,
write
ma'am.
the answer here. Yeah, 11.2 centimeter cube. So if you have consumed 11.2 centimeter cube, then uh, yeah, exactly. Then this like it's a continuation question. It's not a separate question. So in this case, can we achieve the target growth rates? No, right? Because we are allowed to by the flow controller, we are allowed only 1000 centimeter cube per minute, but we need 1000 uh, 11,000 share 1120 centimeter cube per minute. So this is not feasible. Okay, so again this is also a continuation. In the previous case that we saw that in a hot wall furnace it was not feasible to get so much uh, volume of diluted silane. So let us try to go to the cold wall CVD system by switching out the resistive coils with inductive heating coils. So in inductive heating coils we are not actually heating the entire furnace, we will be only heating the substrate that is inside. Also we reduce the number of wafers to 1. So we only have one single wafer. So basically we have reduced the area over which the silicon will get deposited. So rest of the things remain same. We can achieve achieve the intended growth rates? So let us calculate the new area. So the area of deposition of silicon. So this will again be just pi r square and into 2, because both sides of the wafer will get deposited. Let us assume that. So both sides are getting deposited, then we have to put 2, and r was how much? 7.5 by 2 square into pi into 2. So this will give us somewhere around 88 centimeters square. Okay, so now the area has reduced. Again we have to do the exact same thing that we did in the previous question. We have found the area. So what is the volume of silicon that is deposited? Again, so we are giving 200 nanometer thickness in 1 minute. Sorry, so this is just nanometer. Okay. So 200 nanometer times 88 centimeter square. So that will give me, converting to proper units, it will give me somewhere around 0.0018 centimeter cube per minute. So that is the volume of silicon deposited. Next thing is, we, again we are not asked the volume of silicon. We have to find out how much SiH4 we require. So for that we first convert this volume into the number of molecules, the number of silicon atoms. Uh, so that we can simply do by, or SiH4 atoms required will be, so if you remember the density I wrote in the, so that is 10 power 22, right? So 10 power 22 atoms are present in 1 centimeter cube. So how many in 0.00, let me just put it as 2 centimeter cube. So that will be 2 into 10 power 19 atoms or molecules, because I am writing SiH4. So 2 into 10 power 19 molecules means how many moles? 2 into 10 power 19 divided by 6 into 10 power 23, that is the Avogadro number. That will be nothing but 3.3 into 10 power minus 5 moles. And we know that 1 mole requires 22.4 liters. So 3.3 into 10 power 5 minus 5 moles will require volume of SiH4 required is nothing but 3.3 into 10 power minus 5 into 22.4, and now this is 22.4 liters. I will just directly convert it into centimeter cube by multiplying by 1000. So that will give me something around 0.75 centimeter cube. So I am just directly writing answers here, you can verify them, right, you can verify them later. This is just what I did.
Ma'am, one question. Um, Not about this actually. One question is like that APCVD system is having a hot wall or cold wall?
Are you asking me from
And
the
furnace.
quiz?
Yes, ma'am. Actually, there it is written a hot walled APCVD furnace.
Is it? I'll just check the quiz.
I'm not asking whole concept, but just starting one. A hot walled APCVD furnace.
Okay. APCVD can have both hot and cold walls, I think. Wait.
But how?
Like we can do with a cold wall APCVD, but if you want, like, cold wall is sufficient for APCVD, but we can go for hot wall also, I think. Anyways,
Yes,
which question
but
is it?
ma'am, fifth, sixth, seventh. But ma'am, the question is like that. Suppose if you will consider the hot wall furnace, then the area of furnace will come into picture and area of wafer will also come.
Exactly.
Both will come.
Yeah.
So
So that doesn't depend on APCVD or LPCVD, right? If it's hot walled, everywhere it will get deposited.
yes, ma'am. So
Uh,
again, question then why they written over APCVD?
uh,
That's the question.
uh, okay. So what if it, what like your point is, if it is APCVD, so we are doing it at atmospheric pressure. So that should not matter, right? If you are doing it in hot walled container, I think it should be still deposit everywhere.
So according to you, is it confusing?
It's not like it is confusing in the sense that uh, we are more used to having APCVD with cold wall, because that
Yes.
was what was told in the class, right? But
Yes.
but the point there was we don't need a hot wall for APCVD because it's not that temperature critical. However, having a hot wall is a added benefit, like even though it's not that temperature critical, you can always have a more temperature control, right? Like it's not doing any harm. So I think it is okay. We just what are they asking? But
Yeah, means I just started reading the question, na?
okay,
So I just saw the hot word APCVD furnace. That's why I'm
that's
asking.
why I got confused.
Hmm.
Okay, like even I don't know the answers, so I should not comment. Like,
No, no, no issue. Just starting question.
okay, okay. Oh, shit. Right. So let's go to the next question. Like even in this case, we started with a LPCVD furnace, but then in this question, if you see, uh, we are making it a cold walled CVD system. So we are changing it from hot wall to cold wall. So it is possible to change. That is not the point. It is like it is just better to use a hot wall system with LPCVD, and we can go for a cold wall system with APCVD like that. Uh, yeah. Unfortunately, the change from hot wall system to cold wall system led to an issue. The solution of that issue was to increase the temperature to 1000 Celsius and tilt the sample holder at 3 degrees. Can you guess the issue? So we first had a hot wall furnace with 10 wafers. Did someone comment? No. Okay. So first we had a hot wall furnace with 10 wafers, but now, uh, so now that is not the case. We just have a single wafer, I think, and it is cold wall. So the outside temperature is not hot, like the furnace temperature is not hot, just the wafer temperature we are changing. So, but that caused some problem, because of which they had to increase the temperature to 1000 Celsius and tilt the sample holder at 3 degrees. So, they had to tilt this sample and also increase the temperature. So, what can be the issue? So, the usual issue with cold wall systems is that the temperature uniformity is not there. So, in this case what might have happened is uh, so since we were in the rate like if you remember, we started with this graph, right? So we were in the reaction rate limited regime. We were working in this regime. So in this regime the temperature is very critical. So when we go to the cold wall furnace, the temperature was not that uniform, because for high temperature uniformity we need hot wall furnace. So we cannot anymore operate in this regime. So we have to go to high temperature regime, that is the mass flow limited regime. So that's why they went to 1000 degrees Celsius. And next point was about the tilt, right? So they had to increase the temperature and also tilt the sample order. So what happens when we are in the mass flow limiting regime? So if this is my surface and these are my precursors, so my precursors are flowing. So the precursors are in the gaseous state, right? So whenever they are flowing, what will happen is there will be a barrier layer that is created of precursors on top of the surface. So this is because of the no slip boundary condition. So the velocity of gas in the center of the chamber will be very high, but whenever it is close to the surface, the velocity will go down to 0 or very low velocities. So because of that, there will be a very low velocity gas movement near the substrate. So that will create a boundary layer. To avoid this boundary layer, they will just tilt the substrate a little bit. So tilt the wafer like here they are tilting with 3 degrees. So, all these things are suggesting that they went to a mass flow limiting regime. Growth regime. And why did they have to do that? Because there was no temperature uniformity. For cold walled systems. Now going to 1000 degrees Celsius will cause its own will change some things, right? The increase in temperature did not come for free. The increase in temperature further increased the requirement of SiH4. So why is that the case? If you just again go back to the graph, when I am going to 1000 degrees Celsius temperature, the growth rate has grown to somewhere around 0.7, that is 700 nanometer per minute. So earlier we were at 200 nanometer per minute, somewhere here. Now the growth rate itself has gone to 700 nanometer per minute. So if the growth rate is high, then obviously we will need more SiH4 per minute, right? So the SiH4 centimeter cube per minute will go high. Now again we need more precursor. So now we have to calculate how much more of precursor is required, and can we still use the 1000 centimeter cube per minute mass flow controller. So are you guys following? Okay, I'll proceed. So so now the growth rate is 700 nanometer per minute. So it is so for 200 nanometer per minute, we found that the amount of silane required was the volume of silane required was 0.75 centimeter cube, right? Or sorry, yeah, this is the number, right? It was 0.75 centimeter cube. So what is it for? Okay, one thing I forgot to mention here. Even though the volume of silane required is 0.75 centimeter cube, which is lesser than previous time, the actual volume will be, so since there are if there were 10 wafers, it will be 7.5 centimeter cube. No, wait. So yeah, sorry. So this is 0.75 centimeter cube, but this is the minimum volume that is required. However, we need 10 times of this, right? So in the previous case also, we saw that we need to flow 10 times of this minimum flow rate, and also the SiH4 is 10% diluted. So we need to multiply this number by a total of 100. So that will be some 75 centimeter cube per minute. So this is in the case of cold wall furnace. We require so much, but now the cold wall furnace, we have increased the temperature to 1000 Celsius, so that we can work in the mass flow limiting regime. So that has caused us to have a higher what rate of deposition. So that's why earlier it was 200 nanometer per minute, and in 200 nanometer per minute we require 75 centimeter cube volume of SiH4. So for 700 nanometer per minute we will require 75 into 7 upon 2, right? 700 by 200 basically nanometer. So we can just say 7 by 2. So that is nothing but 262.5 centimeter cube per minute. So, if you look at this number, this is still less than 1000 centimeter cube per minute. So, it was beneficial to go to the mass flow limiting regime, even though while going to the mass flow limiting regime we had to increase the temperature, which increased the growth rate. However, the net result was not that high, and therefore, the volume that is required is 262.5 centimeter cube per minute. In the previous case, it was when we were not in the cold wall furnace, we were in the hot wall furnace, it was 1120 centimeter cube per minute. So, which was not feasible. However, now it is less, so it is feasible. I hope I am making sense. So, any doubt in this series of questions, or shall I move ahead? Okay, I'll move ahead. So, yeah, so it's multiple choice question. For epitaxial oriented and lattice matched with substrate crystalline film deposition of silicon of controlled thickness using chemical vapor deposition, the gas flow in the deposition chamber should be kept in which regime? So, this is very trivial. So, yeah, so for CVD we generally keep the gas in which regime?
It laminar flow.
Yeah, laminar flow. So, one thing that you might get confused is viscous flow, because laminar is also a type of viscous flow, but then just remember that turbulent flow is also a type of viscous flow. So we don't want turbulent flow, we just want the laminar flow, right. So the next one, for a CVT system, the mass transfer coefficient H, so this is the d by delta that was discussed in class, basically Henry's coefficient I think, that is 10 centimeter per second, and the surface reaction rate coefficient is so much. So for any CVT system we know, right. So one thing is how the precursors diffuse to the substrate. So this is the gas and this is the substrate. So how does the gas diffuse to the substrate, and like how fast is the reaction at the substrate. So these two things govern the CVD process. So at 900 Celsius, so they have given us the temperature. Which tube is suitable if thickness uniformity is desired? So okay, so the furnace, we have hot walled furnace or cold walled furnace, right? So should we use a hot walled furnace or a cold walled furnace? To decide that, we first have to decide if we will be operating in the reaction rate limited regime or mass flow limited regime. So in this case they have given us the different coefficients. So based on these coefficients we can check if we are operating in reaction rate limited or mass flow limited regime. So at 900 Celsius, what is the value of K? H we know is 10 centimeter per second. K we have to calculate. It is 10 power 7 into e power minus 1.9 eV by kb they have given 8.61 into 10 power minus 5 eV, and temperature they gave 900 Celsius, that is 900 plus 273, yeah. So after doing all this we can get the value of K, and K should come out to be somewhere around 0.066 centimeter per second, and H is 10 centimeter per second. So based on these two rate coefficients, what do you think, will we be in mass flow limited regime or reaction rate limited regime? So K is surface reaction rate coefficient, H is mass transfer coefficient. So H is more, right? So that's why we will be in which regime? So H is more, that means mass flow is easy, right? The rate of mass flow is like the mass transfer coefficient is high, that means the diffusion of gas is not the problem. The real problem here is that the K is very small, that means the surface reaction rate coefficient is small, that means it is limited by surface reaction rate. So now that we know that we are in the surface reaction limited rate, so the growth is limited by the surface reaction rate. So then in this regime we know that it is very temperature critical. So if it is temperature critical, we want very good temperature control and very good temperature uniformity. So the temperature should be uniform throughout the furnace. So then we will use hot wall furnace. It's okay. Okay, so the next problem, during deposition of material in a CVD process, conditions at the reaction surface are at equilibrium, at supersaturation, at undersaturation or unknown. So, okay, suppose this is my substrate and I am depositing on this substrate. So, for deposition to happen using CVD, some amount of precursors should come to the adsorb to the surface, form a layer, and obviously whenever something is coming and absorbing, the same thing can also desorb. So, if the reaction is at equilibrium, the adsorption of precursors and desorption of precursors will be also at equilibrium. So, then there will be no film that will be deposited. So, how much ever is coming will also go. So, at equilibrium is not the correct choice. At supersaturation, however, what happens is we have more adsorption compared to desorption. So, near the surface or the reaction surface, there is a lot of precursors that are available, and so that is what is called supersaturation, right. So, then there will be nucleation and everything, all the rest of the processes will follow only when there is more adsorption compared to desorption. So, that is why for CVD to happen, we need the surface to be at supersaturation. Next, APCVD is commonly used in which regime? Yeah, just like we discussed before, APCVD will be commonly used in mass transport limited regime. LPCVD will commonly use in surface reaction rate limited regime. On an amorphous substrate, higher nucleation density translates to okay. So, say this is my substrate or the wafer, it is amorphous. Now, if there is higher nucleation density, what does that mean? There are lot of nuclei forming, and now they will grow to form grains, right. So, what usually happens in a CVD process is first we form a nucleus, and then on top of that nucleus the reaction continues and we start to forming grains of the material that we want to deposit. So, if the nucleation density is very high, all the nuclei will be so close that the grain size will be lower, right. So, to have higher grain size, we need nucleation density to be low. Then the individual grains will have, like here one grain will be this big, other grain will be this big. So, yeah, before they merge they will have a lot of opportunity to expand. So, like just by intuitively we can see that higher nucleation density means lower grain size. At high partial pressure of SiH4, silicon epitaxy growth rate is often limited by. Yeah. So, this was discussed in class, like exactly this topic was focused. So, what happens at higher partial pressure is we have lot of SiH4 and we are having a silicon substrate and we are depositing silicon on top of silicon substrate, and that is like we have to deposit it epitaxially. So if we have a lot of what is happening is, this is silicon. So at the surface there will be some silicon dangling bonds. So some of the silicon won't have their valencies satisfied. So there will be those dangling bonds will be there. And for those dangling bonds to be satisfied, we are flowing this SiH4, and we expect that the silicon will sit on silicon and the H4 will go as H2 gas. But what might happen is, at very high partial pressures of SiH4, some of this hydrogen can go ahead and bond with silicon. So silicon hydrogen bond will be formed, and the surface will get passivated. So that is not desirable, right? So we want this hydrogen to dissolve from the substrate. So but what will happen at higher partial pressures, that this might happen, and that is causing that is limiting the silicon epitaxy growth rate. So the desorption of hydrogen from the surface limits the growth rate. Okay. If the thickness of a deposited film is 10 nanometer in the center and 5 nanometer at the edge, the deposition was non-conformal, poor in step coverage, non-uniform and non-repeatable. So the point of conformity and step coverage comes when we have a step, and like we can have two types of deposition, right? We can have like this, or like this, like exactly same. So if it is following the boundary exactly, then we call it as conformal. And like this, step coverage is also means approximately the same thing, that it is covering the entire step, and like it's not like this. So this is good conformality and good step coverage. However, in this case what they are saying is, we are depositing on a wafer, uh, so and the deposition thickness is like deposited 10 nanometer in the center, 5 nanometer. So it's thicker here in the center region and thinner at the edge region. So that is, so since we have deposited only on one wafer, there is no way of talking about repeatability. So it is basically non-uniformity. The deposition is non-uniform. Perfect conditions for silicon epitaxy are: so the answer for this is low growth rate and high temperature. Uh, what happens at low growth rate is, there is when the growth rate is low, the nucleation will also be very low, and then there will be time for the like for the nuclei to settle down. So that's why we also have high temperature. So the quality of the film will be very good when it is at high temperature. In instead of this, if we were in some other regime, say high growth rate and low temperature, high growth rate and high temperature, then there will be lot of nuclei, and they won't be like, we will have very sharp grain boundaries, and the defects at the grain boundaries will be very high. So that is not preferred. So we prefer high temperature, because at higher temperatures we will have better quality films, like more smoother grain boundaries kind of, and we prefer low growth rate, because in this case the nucleation will be low, and therefore there will be less grains that are formed. So perfect conditions for silicon epitaxy are low growth rate and high temperature. That's it for today. Uh, if you guys have any questions, you can mail me, or you can ask right now also. Yeah.
Ma'am, please upload this today only. We'll see once more.
Yeah. I'll upload on YouTube. You have the link, right?
YouTube in the review assignment.
Yeah, it should be there. I'll just check. Here they have given this link, right? Problem solving session link. Yeah. So there, like here only I'll upload the week 4 link and the link to the folder from where you can download the presentation.
Yes, ma'am.
हाँ कम okay. Okay, thanks. Thank you for attending. I'll stop the recording and I'll close the session.
Thank you, ma'am.
Thank you.